Welcome to part 2 of my series of presentations about the best methods to alkylate alcohols. In this video we'll have a look at some other electrophiles that can also be used to prepare ethers from alcohols. Because this is not an easy reaction, it may sometimes become necessary to screen more exotic electrophiles if a given etherification does not proceed as expected, and here I'll show you a few. Alkylations with carbonates have been investigated more thoroughly in recent years because carbonates offer a number of advantages if compared to alkyl halides, sulfonates or sulfates. Carbonates are weak alkylating reagents only and therefore less toxic than alkyl halides. Moreover, no corrosive halide waste but only carbon dioxide and an alcohol are generated as byproducts. Because carbonates are much less reactive, however, high concentrations and reaction temperatures are often required. Alkylations with carbonates can be catalyzed both by acids and bases. In this example, it was attempted to use an acidic ion exchange resin to promote the ethylation of octanol with diethyl carbonate. Unfortunately, this did not work well, and a number of byproducts such as other carbonates and symmetric ethers were also formed. In this example, however, the ethylation of salicylic acid with a large excess of diethyl carbonate proceeded cleanly, and even the carboxylate was ethylated. The reaction was conducted under basic conditions and in the polar aprotic solvent dimethylacetamide. This example is similar to the previous one and shows that phenolates can be alkylated by carbonates even at temperatures as low as 100 degrees Celsius. The complete dealkylation of a terz butylsulfonamide also took place, though. Allylic and propagyllic carbonates, esters, and even alcohols are reactive electrophiles with a high tendency to form stabilized carbocations, similar to benzylic electrophiles. The formation of propagyllic carbocations can be accelerated even further by copper catalysis, as shown here. Copper salts and terminal alkynes yield copper acetylides that can form well-stabilized carbocations. In this example, catalytic amounts of an enantiomerically pure copper complex were used to propagylate methanol enantioselectively. Because in palladium allyl complexes the metal is closer to all three carbon atoms than in copper acetylides, palladium-catalyzed allylic substitutions can proceed with much higher enantioselectivity than that achieved in the previous example. Here, a primary alcohol was allylated by an allylic acetate in high yield and with 99% enantiomeric excess. An allylic carbonate would probably give a similar result. Another class of compounds that can be used to alkylate alcohols are benzylic or allylic imidates. I could not find any example of alkylations with simple aliphatic imidates, but some of them may also work under optimized conditions. In my videos about the preparation of alkyl chlorides from alcohols, there's a chapter about the use of imidates as intermediates. Thus, these intermediates are reactive enough to alkylate even chloride, which is a rather poor nucleophile. Imidates can be prepared in a number of ways. One method is the addition of alcohols to electron-deficient nitriles. Imidates become more electrophilic upon protonation and are usually used for alkylations under acidic reaction conditions. The reactivity of protonated imidates is similar to that of the cationic alkoxyphosphonium salts formed during the Mitsunobu reaction. The main difference is that alkoxyphosphonium salts react exclusively with negatively charged nucleophiles, because the nucleophile must form a covalent bond to phosphorus before displacing the phosphine oxide intramolecularly. Protonated imidates, on the other hand, react not exclusively but only preferentially with anionic nucleophiles, and can also be used to alkylate neutral nucleophiles, such as for instance anilines. Similar to imidates are ureas alkylated at oxygen, which can be formed from alcohols and carbodiamides. A third strategy is the reaction of alcohols with chloroiminium salts, such as the Wilsmeyer reagent. With this strategy, there will always be chloride in the reaction mixture, and because of the preferential alkylation of anionic nucleophiles by protonated imidates, alkyl chlorides can be formed as byproducts. Another type of electrophile with a similar reactivity as protonated imidates are 2-alkoxypyridinium or quinolinium salts. These can be prepared by aromatic nucleophilic substitution or from 2-alkoxypyridines. One potential side reaction of the use of imidates as electrophiles is the isomerization to N-alkyl amides. In the case of allylic electrophiles, this rearrangement occurs particularly easily and with allylic inversion. This here is an example of the use of a Vilsmeier reagent-derived imidate of an aliphatic, non-activated alcohol for the intramolecular alkylation of a phenol. Intramolecular reactions are, however, much faster than intermolecular reactions, and it is not clear if intermolecular versions of this reaction will also give such a high yield. In this example, a tertiary benzylic alcohol was converted into trichloroacet imidate by treatment with trichloroacetonitrile. This imidate could be used to alkylate alcohols in the presence of catalytic amounts of a Lewis acid. No elimination occurred, and high yields of the ethers were obtained under mild conditions. Here, these mild conditions were used to etherify the natural immunosuppressant ascomycin, again with a benzylic imidate. In order to prevent multiple alkylations and a byproduct formed by Friedel-Crafts alkylation, an excess of ascomycin was used and recovered after the reaction. Despite the structural complexity of ascomycin, the desired ether was obtained in 55% yield. Beta-hydroxynitriles or carboxylic esters, such as derivatives of serine, are particularly difficult to etherify under basic conditions because the products readily undergo elimination. In this example, such an etherification could, however, be achieved by using a 2-benzyloxypyridinium triflate as electrophile and a weak base only. Epoxides can act as electrophiles both under basic and acidic conditions. Upon reaction with nucleophiles, a new alcohol is formed, and if the concentration of epoxide is too high, it can polymerize. In this example, butanol was alkylated with the aid of alumina as catalyst under almost neutral reaction conditions. The yield was high, but the regioselectivity was low. Higher regioselectivities were attained in these examples here, where the alkylations were conducted under slightly acidic reaction conditions. Acid catalysis seems to be the better strategy for the alkylation of alcohols with epoxides. Diazoalkanes are one further type of electrophile suitable for the alkylation of alcohols. Diazoalkanes can be prepared by the oxidation of hydrazones and by the base-mediated cleavage of sulfonyl hydrazones or N-nitrosoamides, carbamates, ureas or sulfonamides. Only diazoalkanes that cannot eliminate nitrogen are stable at room temperature, whereas those capable of being converted into olefins by nitrogen elimination are only stable for a few hours at temperatures below -70 degrees Celsius. Diazoalkanes are slightly basic diazonium ylides and must be kept away from acids which would protonate the diazoalkane and convert it into a highly electrophilic diazonium salt. The latter can also be generated directly from primary amines by treatment with nitrous acid. Aliphatic diazonium salts have short half-lives only and spontaneously fragment into nitrogen and a carbocation. These will immediately react with any nucleophile available or rearrange to more stable carbocations. Deprotonation of such carbocations can yield olefins or even cyclic products. Because of the high energy of these carbocations, product mixtures often result and the yield of single products is only low. Diazoalkanes can also react with alcohols under basic conditions and with the aid of various catalysts. In some instances, high yields have been achieved, in particular with diazomethane or phenyldiazomethane, but with other diazoalkanes, yields are often low. Much more stable than simple aliphatic diazoalkanes are those with electron withdrawing groups attached to the nitrogen-bearing carbon atom, for instance diazoketones or diazoesters. These can be stored at room temperature for years and only react with alcohols in the presence of strong acids or transition metal catalysts. One exception is diazoacetonitrile, which is volatile and tends to explode when it condenses in pure form on cold surfaces. Typical side reactions of the alkylation of alcohols by diazoalkanes is the cyclopropanation of olefins, alkynes or arenes, CH insertion reactions, oxidative hydride abstraction, and the formation of ylides upon reaction with pyridines or thioethers. This is an example of the methylation of a secondary alcohol, dihydrocholesterol in this case, with diazomethane. A catalytic amount of tetrafluoroboric acid was sufficient to bring about a complete methylation. Similar reactions have been catalyzed by boron trifluoride etherate, aluminum chloride or silica gel. These here are attempts to alkylate benzyl alcohol with less stable diazoalkanes than diazomethane. Only low yields of the expected ethers were obtained. Because these diazoalkanes are unstable at 0 degrees Celsius, I would have chosen a much lower reaction temperature and a less reactive solvent, for instance dichloromethane. This is an example of the alkylation of menthol with a diazoketone, catalyzed by indium triflate. Despite the use of toluene as solvent, a high yield of ether was obtained. Again, even better results may be obtained in a less nucleophilic solvent, such as chlorobenzene or dichloromethane. Dichloroethane is also better suited as solvent for reactions with powerful electrophiles. Here, a diazoester was converted into an isopropyl ether enantioselectively with the aid of a chiral copper complex. Instead of isolated diazoalkanes, their precursors can sometimes also be used directly to alkylate alcohols. In the seminal article of Bamford and Stevens, the reaction of sulfonyl hydrozones with alkoxides was reported. When elimination wasn't possible, ethers were often obtained as main products, as in this example. Unfortunately, a number of byproducts were often formed, including a sulfone resulting from the alkylation at sulfur of a sulfinate, as well as carbene dimers and azenes. At lower temperature and with a slight excess of alkoxide only, better yields of ethers can sometimes be obtained, as in this example. Even alkali carbonates can be used as bases because no deprotonation of the alcohol is required. On this and the next slide there are some more, mostly recent examples. You can find this list of references also in the description of this video. The next presentation of this playlist is about the alkylation of alcohols with alkenes. These reactions are particularly important for industrial, large-scale processes because no stoichiometric waste is formed at all. So long.